0.606 times 25 degrees C. Okay, so that will give us the velocity at 25 degrees C. This will be the velocity of the sound will be 0.606 times 25 plus 331.5, and that will be 347 meters per second. Okay, now what do we do? Well, we have the velocity of sound. Now we need to use the Doppler shift equation. The Doppler shift equation, remember, is the frequency observed is equal to, it's the ratio. And that equation is back on page 361. 361, and it's the velocity of the sound plus and minus the velocity of the observer divided by the velocity of the sound plus and minus the velocity of the source times the true frequency. Okay. All right. Well, is the observer moving? You are the observer. You are staying put. You're not moving at all. So this is 0. Okay. The velocity of the source is moving. It's moving away from you. Since it's moving away from you, the sound is going to go lower. So we know we have to use the plus sign down here. So we plug this in. Can you see way down here? I think so. It would be 347 divided by 347 plus 25.6. Notice both the numerator and denominator are in meters per second. Notice the units cancel out, which they should. And F true, this is F true, the sound of the flute, is 278 hertz. So we would get, so really it's just a ratio times 278. Okay, so it's 347 plus 25.6 divided by 347. So I calculate this ratio and then I multiply that by 278, and I get 259 hertz. So the pitch, 259 hertz, so the pitch has dropped. It dropped from 278 hertz down to 259 hertz. Okay. All right. That's number 6. Okay, number 7. A car's horn normally blows at a constant frequency of 551 hertz. So we might say, oh, that's probably F true. That's normally what it is. So that's the true frequency. You are standing in your yard and you hear the horn, but what you hear is 578 hertz. Okay, that's what you hear. The question is, what is the speed of the car moving? Again, T is equal to 25 degrees C. The question is, what is the speed of the car? What is the car speed? Now, it didn't say how fast are you moving. You, the observer, are assumed to be 0. So the car, so that will be the source is moving at what velocity? Okay. Well, again, we first have to know what the velocity of the sound is, using the old equation we know, 331.5 plus 0.606 times t, and we're going to substitute into here 25 degrees C. We will get a velocity of, in the sound, at 25 degrees C, the velocity of the sound is 0.606. Let's see, I would get 347. I think we calculated that before. That's the velocity of the sound. Okay. Now what do we use? We use it, well, we have to use the Doppler equation. Doppler equation is that the observed frequency is the ratio, in this case, the observer speed is 0, so we simply have the velocity of the sound divided by the velocity of sound plus the velocity of the source times the true the true frequency. So we have to solve. This is a little bit different because we have this, we have that, we have that. We have to solve for the velocity of the source. So we have to do some algebra. So let's come over here. F observed divided by the F true. That ratio is equal to the velocity of the sound divided by the velocity of the sound plus the velocity of the source. Okay? We have to solve for this. So let's come over here and we'll say we'll multiply by, well, you could do a number of things. Let's multiply this over there, the denominator, so we'll get, actually I'm going to tell you what, I'm going to come over here. I should have made more room here. I'm going to come over here and say F observed divided by F true. Let's see, I hope you can see me, times V sound plus V source equals V sound. Okay, I want to solve for V. Well, I want to solve for V source. Okay. So how do I do that? So I'm going to have to multiply through here. So I'm going to have this ratio, F observed over F true times V sound plus F observed over F true times V source, I'm going to abbreviate that source, well, equals V sound. I'm getting a little bit messy here, actually, in my writing. Okay, but basically, I should have put that over here. So I'm going to subtract this over here, and I'll get F observed over F true times V source equals the velocity of the sound velocity minus this ratio. Okay. So I've solved for this term, which is this term right over here. Now I'm going to multiply by this ratio, but I'm going to multiply, take this ratio and take the reciprocal of it, multiply it, so I will get V source equals this ratio, but the reciprocal of it, I take the reciprocal of it, multiply it through, so these cancel out, and I get, remember this now, I have to multiply by the whole right-hand side. The whole right-hand side is V sound minus F observed, F true, times V sound. Okay. Looks a little complicated, but I think we can, I hope you can see all of this. What I'm going to do here is I'm going to multiply through here, and I'm going to get, let's see, can you all see down here? Maybe I should probably write that up here. Let me write this off to the side. That F true equals, 551, F observed equals 578, and V sound equals 347 meters per second. Now I'm going to erase this just because I need the space. Okay, I'm going to take this and multiply it through. So I have V sound. Again, I'm just doing algebra on this right now. Is F true divided by F observed times V sound minus, now notice what happens. When I multiply through on this term over here, these completely cancel each other out, and I'm just left with V sound. Okay? Does that make sense? That multiply this by this term by V sound, then I multiply the same fraction by this term over here, and these F ratios completely cancel each other out. Because if I do over, so now at this point I can factor out a V sound, and I'm left with V sound. I could have factored the V sound out before, but I didn't. Equals, well, excuse me. Oops, that's supposed to be V source, I'm sorry. V source equals V sound times the ratio minus 1. And you can see that when I factored out the V sound, so this, the first term here is this, the second term here becomes a minus 1. So my equation now looks quite easy, finally. I've boiled it down using algebra, and this is how I hope you would do it. Use algebra to boil the equation down to what you need it to be, and then you simply plug in. The velocity, the sound velocity is 347 meters per second. Notice at this point I've plugged it down, I've reduced it down as far as I need to go, and now I just plug in the numbers. So I'm much less apt to make errors, numerical errors here. And 551 hertz divided by 578 hertz minus 1. 347 times, okay, here this ratio 551 divided by 578, and then I subtract 1. Whoops. Oops, I think I may have made an error here, because I get a negative number. This becomes less than 1. Uh-oh. I may have made an error. I may have to redo this. Did I make an error in my algebra? I may have. Let me, uh-oh, my wife's, let's see. You hear the horn, observe 578. Oh, you know what error I made? I know what error I made. I said that the sound is, the frequency is higher, what you hear, so the sound is coming to you. I think we're going to have to go back and redo all of this. I apologize, but maybe we only have to do it a little bit. Let's go back to where I think I made the error. I think I made the error actually at the very beginning. Let's see if we can do this quickly. The frequency observed equals the frequency true times the ratio of V sound divided by V sound, and then we have plus or minus V source. Now, I think the last time I think I used a plus. Well, notice if it's going, I think I used the wrong sign here. I think that's what happened. If what you hear is higher, okay, if what you hear is higher than what it normally is, then that means that this number here needs to be a minus number this needs to be a minus in order to make the denominator smaller. That forces the observed sound to be higher. So I think I had a wrong sign. So when I work through this again, I should have realized this, but I forgot. We'll do this real quickly. V sound minus V source. So we multiply that through, remember. I'm going to just put this ratio through FO over FT is V multiplied by this denominator, V sound minus V source equals V sound. So when I multiply this through and I solve for this, now I think what the problem is this becomes a minus sign. So, well, let's do this. This ratio times V sound minus the same ratio, F ratio, times V source equals V sound. Okay, at this point we solve for V source, which means in order to do that we have to flip this over here, and we're going to end up, if I flip this term over here and this term over here, I'm going to erase this and put it right here. Hope that's not too confusing. But what I will end up with is this ratio minus V sound equals F okay. Does that look right? Let's see here. Hopefully I did it right. Okay. And then I multiply, and I multiply this, and I get multiplied through this ratio, and I get Ft over Fo multiplied by all of what's on the left-hand side, V sound minus V sound okay. Notice the first term, the factors cancel out completely when I get V sound minus F true over F observed V sound equals V source. Now I'm going to factor out the V sound, and I get V sound times 1 minus F true over F observed equals V source. And notice it's the same thing as what I have here, but I have this flipped. So that's why it doesn't make sense. So it's 1 minus F true over F observed. Now it makes sense because I made a sign change. I made a sign error. Okay, I'm going to put in the numbers here, and I get 347 meters per second times 1 minus F true, 551 over F observed, 578. Okay, notice that this will end up being 347 times 1. Now this ratio becomes 551 divided by 578 is 0.953, so it's 1 minus 0.953, I'll say. But when I do that, and then I multiply by 347, I'm going to round to 3 significant figures. I get 16.2 meters per second. So the velocity of the source is 16.2 meters per second. And we finally get the answer. I think that's the right answer, according to the book. So, and we finally did it, but I had made a terrible mistake early on because I had flipped the positive sign, negative sign to a positive sign. So, hope that wasn't too confusing. All right. Okay. Now, that was number 7. Now we're going on to number 8, 9, and 10, the last 3 problems, and these are dealing with light waves. Okay, light energy. The wavelength of indigo light is, 442 nanometers. Remember, nanometer is 9 times 10 to the 9th. What is the frequency? What is this energy? Okay. Well, so the wavelength is 442 times 10 to the minus 9 meters. Okay. So remember that the frequency times the wavelength equals the velocity, but for the speed, the velocity of light is the speed of light. Okay. So the frequency is therefore the speed of light divided by the wavelength, which is the speed of light is 3 times 10 to the 8th meters per second, very fast, divided by the wavelength, 442. So the frequency will be speed of light divided by the wavelength, and I get 6.8 times 10 to the 14th hertz. 6.8 times 10 to the 14th hertz. Okay, and the energy of one photon of light is h times the frequency, that's Planck's constant, 6.63 times 10 to the minus 34 joules per second, very small, times the frequency, 6.8 times 10 to the 14th. Hertz is 1 over seconds. Notice that the seconds cancel out. And times 0.63, and we end up with 4.5 times 10 to the minus 19 joules. Now, if you had done this in electron volts, you could have had the answer in electron volts also. The answer in electron volts, according to what I have, would be 2.8 electron volts. Okay. That's number 8. Okay. Number 9, I think number 9 and 10 are problems dealing with the Einstein's photoelectric effect. Okay, and number 9, the work function, they give you what the work function is. The work function of a particular metal is 5.31 eV, electron volt. What is the lowest frequency of light that will result in electrons being liberated from the metal? Okay, so here's the metal. And you have a photon. So what's the smallest? Question is, what's the minimum frequency? The minimum frequency at which electrons will be kicked off. Okay, electrons will be kicked off. And what is that? What is the wavelength of the light? And what is that wavelength? Remember, if we have a minimum frequency, then we have a maximum wavelength also. Okay. Well, remember now, the wavelength, the energy of the photon, okay, has to have a minimum, whatever the energy of the photon, or let me say this, the kinetic energy of the electron is the energy of the photon minus the work function. That's the work function. So if the bare minimum, if there's just a little bit of energy of the kinetic energy being given off, or essentially if this is just about 0, then the energy of the photon minus the work energy is essentially 0, or said another way, this has to be just greater, equal to or just greater. This ratio has to be just greater. So if you put it as an inequality, like that, okay, then we could say that the energy of the photon must be equal to, or just barely equal to, and greater than the work energy of the metal, okay? So the minimum energy required, well, we know what this is. We know that this is 5.31 electron volt. And remember that the energy of the photon is h times the frequency. So, okay, so what we have is that the frequency must be equal to or greater than 5.31 electron volt divided by Planck's constant. Okay, so the minimum frequency will be wherein these are equal to each other. So it will be 5.31 divided by Planck's constant. Planck's constant in electron volt is 4.41. Whoops, I got that backwards. 4.14. 4.14 times 10 to the minus 15 E. There. 4.14 times e to the minus 15 electron volt. So we take 5.31 electron volts and divide it by Planck's constant. Whoops, pushed the wrong button. And let's see, I get that the minimum frequency is 1.14 1.28 times 10 to the 15 hertz. Rounded off to three significant figures of 1.28 times 10 to the 15 hertz. That wavelength that corresponds to that would be the speed of light divided by this. So I'm going to take that number, and I'm going to take the speed of light and divide it by that number. And I would get a maximum, that's really a maximum wavelength of 2.34 times 10 to the minus 7 meters, which is the same thing as 234 nanometers. Okay, 234 nanometers. So, now, it asks a question, if the light of wavelength, if the light of wavelength that's lower than this is shown in the metal, would electrons be liberated? Certainly they would be liberated. And they would be liberated with higher, the electrons would fly off at higher kinetic energy. Okay.